welcome students, and in this video we are going to talk about Riemann problem. Okay, so in the last video, so this is a continuation of our study of conservation laws, and in the last video we looked at a problem, right, that if you remember, ut plus ux is equals to 0. That's the problem given to us, and u at, let's say, x0 is given to be 1 for x positive and 0 for x negative. Okay, or the other way around also we did, right? So that's not the point. The point is this: see, we want to kind of generalize this problem. Okay, and what we need to do for that is first of all, let us write down the proper Riemann problem. So this is from the earlier class or earlier video, whatever you want to call it. So we consider this problem. So the Riemann problem is for a general problem, right? ut plus f of u, clear, with respect to x, that is going to be 0 for t greater than equals 0 and x in R. Okay, and we also assume u at the point x0 is going to be some phi of x. Clear? Now what is phi of x and all that, we will just write it down. So here phi of x is a very special function. Okay, so this problem is called a Riemann problem. Okay, so let me write it down. Number this is 1. Okay, 1, and phi here phi of x is a piecewise constant function. Okay, piecewise constant means it is something like this. U minus we will write it for x negative, okay, and u plus we will write it for x positive. So basically from left, if you are looking at it, I will call it a u minus, and from right we will call it a u plus. This is some constant, u minus u plus. This is nothing to do with, if you guys know what u minus u plus, there is another notation, right, that if u is a function, u plus u minus. Here we are not assuming something like this. So u plus u minus is a maximum, minima, that sort of thing. It's not there. U plus u minus is some number. Okay, some number. Yeah, so u minus is from left, so x negative, u minus, x positive, we are just assuming u plus. Clear? No information on x equals to 0 is given. Okay, and so this is phi, and what is f? So f here also, f is uniformly, very important. Okay, f is uniformly convex. Clear? F is uniformly convex. That is, okay, what does it mean? It means that there exists, okay, a theta greater than 0 such that, okay, very important, please understand, you guys know all about convexity, right? If f is convex, so let's say if f is a C2 function, or maybe C infinity, let's just stuck with C infinity. F is the C infinity function which is convex. Now we all know that if that is the case, f double prime has to be greater than 0, right? That is convexity. So f double prime can be greater than 0 means, f double prime for some sequence xn, it can happen that f double prime of xn can converge to 0. It can happen, right? It can be as closer to 0 as possible. But if it is uniformly convex, it means that there exists some theta positive, okay, such that f is bounded by that theta. So f double prime is bounded by this theta such that f double prime is greater than equal theta greater than equal 0. So basically it is bounded below by that theta. So it cannot arbitrarily go towards 0. Clear? Okay, so this case cannot happen. This is uniformly convex. This is convex. If f is convex, f double prime is positive. That you guys already know. Here it is called, we are saying more, we need uniform convexity. Uniform convexity is, it is bounded by a positive number, however small it might be. Clear? Okay, now just for fun, you guys can obviously try and find out a uniformly convex. So this the example of this thing I will not give it to you. You guys have to find it yourself. Okay, so so this is for a small exercise for you guys. Exercise: find f from R to R. Of course it will also be in the assignment, but anyways, let's just put it as an exercise here. F from R to R, which is uniformly convex. Okay, of course you do realize that whenever we are saying uniformly convex, we are assuming that f double prime exists, right? So basically, of course, assuming f is smooth, f is at least C2 or C infinity. I mean, here it is not a very, precise thing. You can take C infinity, you can take C2, but for, C2 is fine enough. You don't worry about it. Okay, so let me write it down. So this problem 1. Okay, the problem 1. So basically the equation, this equation along with this data, where the data is, this is a piecewise constant data. Okay, we call it a piecewise constant data. We have looked at two different problems, right, with piecewise constant data. So if the data is piecewise constant and f is given to be uniformly convex, in that case one is called the Riemann problem. Is it fine? It's called the Riemann problem. Okay, this is after the great German mathematician. I am absolutely certain that all of you guys have heard about Bernard Riemann, right? So this is after him, Riemann problem. Okay, so that guy has contribution in everything, it looks like, yes, from geometry to integration to everything, right? Okay, so this is that Riemann. Okay, so let's look at the problem in a more precise way. So essentially we are writing down a theorem. So this is a theorem. By the way, you see, the whole of whatever we did up till here, all the second order equations which we have studied, heat equation, wave equation, and Laplace equation, and now these conservation laws which we are studying, I am doing all of that from Evans. Okay, it's just some precise explanation. Evans' book is not a very easy book to follow by yourself if you are doing it for yourself for the first time. So this is just an explanation, for my explanation, how I understand Evans, and that I'm just writing that down. Okay, so the theorems are exactly like Evans. Okay, so let me write it down. So of course, in this video, whenever we are talking about phi and whenever we are talking about f, these assumptions are assumed. Okay, these are assumed. On phi and f is assumed, right? That until we say otherwise. Okay, so given phi and f, of course f is given to be uniformly convex, if you remember. Okay, given phi and x, there exists a unique, very important one, unique, this means unique weak solution. Okay, unique weak solution. So basically you have two part of the well posedness, unique weak admissible solution. Okay, you guys already know what is admissible solution. So basically the Rankine Huguenot condition is satisfied along with the entropy condition, right? Solution to the Riemann problem. Okay, to the Riemann problem 1 to 1. So basically let me write it as 1. Clear? Okay, so number 1. So essentially what do we have? If u minus, so the wave on the left, okay, is greater than u plus, so the initial condition, not here wave. So basically it is the height of the wave at t equals to 0. Okay, so if that is greater than the height is more than the wave on the right, okay, then the admissible solution okay, has a shock curve. You remember the curve x equals to t? Okay, has a shock curve of speed sigma. Okay, of speed sigma. You remember speed, which is f prime of xi prime of t, right? And the solution is given by okay, so it is basically telling you what is the solution. U of xt is going to be u minus. This is for x less than t sigma. Clear? Okay, and u plus, which is x greater than t times sigma. Okay, now don't get confused here. I am just writing down what we have learned in the we looked at two different examples, right, in the other video. So whatever we have learned from that, I'm just we are taking intuition from there and we are writing down the theorem. We will of course prove this thing. Yeah, so basically what it is saying is for x less than t sigma. So in our earlier case, if you remember, sigma for f is u square by 2, sigma was half, right? So at that case, u is u minus for x less than t by 2 and u plus for x greater than t by 2. You can just compare it with your other example, okay? And number 2, if u minus the wave on the left is the speed is less than that, u plus on the right, then the solution, then you remember what happened? There was a gap, right? That rarefaction gap. Then the solution has a rarefaction wave. I hope you remember this one. Yes, this was the gap was there in that xt plane where we could not find a solution, right? Okay, so that is the rarefaction wave, and the solution is given by, if you remember how we did the solution, so we can write it with the shock wave also, but that was giving us the wrong entropy condition. Okay, so the right entropy condition is given by so the solution which satisfies the right entropy condition is given by, if you remember, that was given by some x by t, right? So here we will write it in a more general way. xt will be given as u minus, clear, for x less than f of u minus f prime of u minus times t. Okay, g, capital G, I will write it down what capital G is. So in our earlier case, the earlier example which we just did, okay, just did means in the other video, the second example, in that case g of xt was actually x by t. Okay, so that was because of our initial condition. Okay, so don't worry about that is just for our initial condition. This is just a general version of that. Okay, so u minus less than x by t less than a prime u plus. Okay, I hope this is fine. And u plus when x by t is greater than f prime of u plus. Clear? So what is g here? Here where capital G is f prime, the inverse of that. Okay, the inverse of that, the inverse of f prime. Okay, fine. Now one question, this is I want you to ask, I will not be answering it right now. Okay, what I want you to do is this. So this is a question for you guys, think about it. Why do you think that the inverse of a prime exists? Okay, we certainly did not start with f is bijective and everything, right? F prime is bijective and all. We did not start. So why does the inverse exist? That is one question which I am leaving it for you guys to think about. Okay, so let's prove this theorem and then we'll go from there. Okay, so proof. So first thing first, the proof. Now, of course, you see the first one, the first problem. See this problem, number one. See, u is given by u minus for x by t less than t and u plus for x by t greater than t. Okay, so do you think it is a classical? You see. In either side of the curve, there is a curve x equals to sigma t. On either side of the curve, this is going to be what sort of thing? This is going to be a classical solution, right? On either side of the curve. Okay, if you remember, so you see, because this is a constant function, right? It's a constant function. It satisfies the, it satisfies the equation. There is nothing to prove there, right? You can just put it there and it's constant. So there is nothing. Whenever you do ut and you calculate ut, and if you calculate ux, it's going to be 0. So you don't worry about all that. It's definitely going to satisfy the equation. That's not a problem. And anyways, they are classical. They are smooth in either side of the curve x equals to sigma t. right? And that will actually guarantee that you have a it's a weak solution. Yeah, why it will guarantee? Because I mean, it will satisfy the Rankine-Hughes jump condition also. Okay, because it is given like this. You see, it is given like this. I mean, yeah, because this sigma is I mean f prime of t. The whole how do I put it? You see, the whole solution is constructed thinking of all of that condition in mind. So definitely this is going to see sigma is what? Sigma is f prime of sorry, not f prime, sigma prime. Sorry, xi prime, xi prime of t. If you remember, okay, that's the speed, right? Okay, so you see what is happening here is this. I mean, the whole if you think about it. This whole solution is set up in such a way that it has to satisfy the Rankine-Hughes condition. This is the Rankine-Hughes condition, right? I mean, if you want, you can just write it down: f of u plus f of u minus by u plus by u minus. That is f prime of t. Okay, so all of that is already satisfied. So this is going to be a weak solution. There is nothing to prove here. Okay, and of course. Yeah, so and why it satisfies the entropy condition? Because u minus is greater than u plus. It is given here. The entropy condition is given here. Okay, so it will satisfy the entropy condition. So I mean, what I am trying to say is this: I am going to skip the first problem. It is not a very difficult thing to see, and I am quite sure you guys can understand that. Okay, this condition, why we need it? This is just to guarantee the entropy condition, and this I mean, after that, whatever the solution is, that is that is actually constructed keeping the curve of discontinuity in mind, so that the Rankine-Hughes condition is satisfied. I hope this is fine. Okay, now let's look at the second problem. That is important. Okay, second problem is important, and let me prove that part. Okay, so the second, let me write it down. It will be better. U of xt. So I want to show this is our weak solution. Okay, this is our weak solution. U minus for x by t less than f prime u minus g, capital G of x by t. Okay, this is for f prime of u minus less than x by t less than f prime of u plus. Okay, and u plus for x by t greater than f prime of u plus. Okay, g is, of course, if you remember, we wrote it as f prime, the inverse of that. Okay, where right now what we are going to do is basically we need to check that you see, first thing first, let's say, I mean, if you draw this x by t kind of thing. Okay, let's say I'm drawing x t, and let's say this is our curve. Okay, x equals to sigma t. Okay, and I mean, we did this sort of thing. So basically, sorry, let me draw it like this. Okay, let me draw it like this. See, for x less than, so let's say this is the part. Okay, this is the place where it is u is g by x by t. Okay, so u equals to g of x by t in this place. So u is u plus here, and u equals to u minus here. Okay, I'm just drawing something randomly. Yeah? This is nothing, I mean, it's not like a precise thing, something in this. Let's say that is your x by t equals to f of f prime of u minus. Okay, and this is f prime of u plus. X by t equals to f prime of u plus. Okay, so I mean, of course, I'm just arbitrarily just drawing some stuff, and here you see in this part of the domain, u equals to u minus. So that's a classical solution in this part. Again, u equals to u plus in this part of the domain. Okay, so that's a classical solution. So we are only interested in finding out if this is valid or not. Okay, so basically we are looking at the left of this particular thing, and on the right of this thing. So this region R, let's call it R. Okay, so we need to check. I hope this is fine. U is a solution in this place, f prime u minus less than x by t less than f prime u plus, because the other two parts, they are classical. Okay, now let's just do that. So how do you check it? It is if it is classical solution, this has to satisfy ut plus f of ux, right? So what is it? It is, the first thing first, we have to use chain rule here. So u is g by x by t, so it is g prime of x by t, and then the derivative of t, so which is minus x by t square. Chain rule, clear? Plus the derivative of this thing, this is f prime of ux. Okay, so ux is g of x by t, clear? G of x by t times ux, right? F prime of u times ux. Okay, see, f of u, the derivative of that is f prime of u times ux, right? Okay, so I'm just writing it down. So f prime of u is g by x by 2, and then ux is g prime of x by t, and the derivative of x by t, which is 1 by t. Okay, derivative of x, I mean x by t with respect to derivative with respect to x, that is 1 by t. I hope this is clear. Okay, so now you see what is happening here. Let us write it down. It is g prime of x by t minus x by t square. Okay, and you see what is g? G is f prime inverse, clear? So f prime of f prime inverse x by t. Okay, so that is 1. So it is essentially, I am left out with g prime of x by t times x by t square. Okay, so x by t from here it is coming, and 1 by t from here it is coming, so essentially x by t square. Yeah, I hope this is fine. Okay, so yeah, now what do we have? Okay, what do we have? So this is basically the same here, so this is 0. Clear? Okay, therefore u is classical in all the three, classical in each of the three regions, right? Each of the three regions, in each of the three regions, where it is defined. Okay, now, so also, okay, along the curve x by t equals to f prime u minus, this curve f prime u minus. Okay, g of x by t, clear? This is f prime inverse of x by t. Okay, that is given by u minus, clear? See, x by t equals to f prime u minus, so f prime inverse of x by t is u minus on that curve. Okay, along that curve, this curve. Okay, now along this curve, now we just I mean, you can do the exact same thing. Yeah, you can do the exact same thing along this curve. You can show that g by xt is u plus. Clear? Okay, therefore u has no curve of discontinuity, so u is continuous, right? No curves of discontinuity. Okay, and thus satisfy the entropy condition. Okay, and that satisfies the entropy condition. Okay, so and now so yeah, it is done. So it satisfies the entropy condition. There is no I mean and it is classical in each of the regions R. So I mean, there is nothing else to do. It is going to be a weak solution. Okay, hence therefore I mean, I don't have to write it. So hence u is a weak solution, and we are done. Okay, so maybe I can end it here. Okay, the theorem. Yeah, I hope this is clear. Nothing to do here. Actually, you see, the point of all of this is the solutions here in both the cases were constructed in such a way that, you know, how do I put it, that you know, whatever we want the solution does. You know, the solution, we are actually manipulating the solution. That's the point. You do understand? So that is why it is bound to satisfy. We have manipulated the solution, and here also we did the exact same thing. It's just a little complicated here because of the capital G. Otherwise there is nothing else to do. Okay, so it is a, I mean, the rarefaction, the solution is a rarefaction wave in that case. Okay, of course it is the admissible solution. Okay, it's the admissible solution. So now we are done. Okay, so you see we are done here. Okay, so let's finish the proof here. Okay, and let's look at one another example, and then we are going to finish this lecture. I think this example will make things more precise. Okay, that will be better. So this is example 3, I guess, of this conservation law. So you have this problem, ut plus ux equals to 0. Okay, u at the point x0 is phi of x. Okay, this is for x in R and t positive. And what is phi? Where phi of x is given to be 1 for x between 0 and 1 and 0 otherwise. Okay, now of course we already know, so this is a Burger's equation. We have solved it many times. We already know what are the characteristics curves. So the projected characteristics, I am not proving this thing here. The projected characteristics curves are given by, so again let me explain to you. In this course we had taken something for always, that as far as I mean in my control I have always used consistent notation. So you see, whenever we write R here, if I am parameterizing a curve C with R, that is always the parameterization of the data curve. Clear? That is always the parameterization of the data curve. So in this case, that data curve will be given by R0 phi of R. Right? R is in R. Okay? And the characteristic curves is parameterized by, so let's say the characteristic curves is given by I don't know, maybe some P, but that is always parameterized by S. Yeah, the characteristic curves are always parameterized by S. So here the projected characteristics are given by x of RT is equals to phi of RT plus R. Okay, and where is this R varying? R is varying in R. Clear? X and T is given to you, and this is the other projected characteristics. Clear? So now let's look at the cases. So case 1. If R is negative, okay, then what is phi of R? Phi of R negative, it is going to be 0, right? It is going to be 0, which implies x is equals to, phi of R is 0, x is equals to R, okay, and what is u along these curves? If you remember, you see, if you remember the characteristics thing, this z prime of Rs, okay, z prime of Rs, this prime is with respect to S, this is equals to 0, right? Okay, so u is constant along these curves, right? And since phi of R is going to be 0, okay, so u is equals to 0 along x equals to R. I hope this is clear. Z is constant. So what is Z? Z is defined by, if you remember, Z of Rs is given by u of x Rs y Rs, right? That is how we define Z. Now you see, Z is constant along S for a fixed R. Z is constant. This is one of the characteristic equation, right? Z is constant along S. At S equals to 0, phi of R, so at when S equals to 0, in the starting phi of R is given to be 0, right? So Z is constant along the characteristic curve, and at the origin S equals to 0, it is 0. So basically Z is 0, and hence U is 0 along these curves x equals to t. I hope this is clear. Okay. Now, if 0 R lies between 0 and 1, then what happens? Then phi of R is going to be, you see, 1, okay, phi of R is 1, okay, and that will imply x equals to, phi of R is 1, so it is t plus R. Clear? And what is u in this case? Phi of R is 1, so initially if u is phi, right? At s equals to 0, u is phi, so z is phi, basically z is u, so hence u is going to be 1 along this characteristic, along these curves, along x equals to t plus R. This is fine, okay. u is constant. Remember, what it does at s equals to 0, goes forward along the characteristics. At s equals to 0, phi of r is going to be 1. So z is going to be 1. So u is going to be 1. Clear? Now, if r is greater than 1, okay, then what is r greater than 1? 0 otherwise, okay. So phi of r is again going to be 0, and that will imply x equals to r, the first case, and u is equals to 0 along these curves, okay, x equals to r, okay. So when r, so essentially what all of this means is when r lies between 0 and 1, okay, x is t plus r. When r lies between less than 0 or greater than 1, x equals to r are the projected characteristics. Clear? Okay. So now let us just draw the the projected characteristic curves, and for that let's just draw it here, right? This is your x, this is your t, and x negative. See, so basically this r is varying in this line, right? X is, so when r is negative, x is equals to r. So essentially it will look like this, no? The projected characteristic comes, it will look like this, x equals to r, okay. And let's say this is your x equals to 1. So for x greater than 1, you have this projected characteristics, which is u equals to 0. So essentially x equals to r here also. So x equals to r. Okay. Now, and r is between 0 and 1. You have x equals to t plus r, okay. So in between r 0 and 1, x equals to t plus 1. So those are lines with slope 1. Okay, so these are the projected characteristics. Now, as you can see that there is a shock. Where is the shock? When this line x equals to t plus r, that for any r, for r between 0 and 1. So basically, let me write it down. So essentially, we have shock, okay, we have shock when the lines x equals to t plus r for r between 0 1 and x equals to 1 intersects. Clear? Why shock? Because suddenly you see you will have for every point here, wherever they intersect, so they are intersecting everywhere, right? I mean from on this line x equals to 1, every point on this line is getting intersected. So if you want to find the value of u there, what is going to happen? That will be a multivariate function, because along these characteristics that is going to be 1, and along these characteristics this is going to be 0, right? So this is kind of a shock curve, you can say, okay. There is a shocking here, okay, and there is a rarefaction wave also. And where is the rarefaction wave? See this part, rarefaction. Why? Because as you can see, you remember the earlier thing, here we do not have any much information, okay. So here we have a blank thing. So this is, and there is a rarefaction wave there. We get a rarefaction wave, okay, where the rarefaction wave between x equals to 0, and x equals to t. Clear? This is x equals to t line, that line, this line. I hope this is fine. X equals to t line. Okay, so x equals to t and x equals to 0. So between this whole thing, there is a rarefaction wave situation going on. Okay, of course this also intersects somewhere at x equals to t equals to t less than equal 1. No? T less than equal, up till t less than equal 1, there is no problem. After that it intersects. Okay, so you have to deal with all of that. All of this issues. So let's do that. So the first thing first, let's just think of a shock curve, okay, which is, since it is emanating from x equals to 1, the shock curve, okay, let's just think of there is some shock curve, okay. So basically let me again draw some pictures here. I hope this will be enough to convince you. This is x equals to 1, x-axis, d-axis, okay, and the shock curve starts from here somewhere, okay. So here it starts from somewhere, so let's just draw it like this. I'm not quite sure what that looks like right now, okay. Let us just do that and then we'll see what it looks like, okay. So you see, of course there are projected characteristics in this part, right? And those projected characteristics, what is u? U in this case is u equals to 0. If you remember, u equals to 0 here, okay. U is 0 and u is 1, u is 0 in this side also, okay. If you remember, see u is 0 along x equals to r, u is 0 along x equals to r for this. So in these parts where they are not touching anywhere, so u is 0, that's not a problem here. Here also there is no problem, u equals to 0. So essentially you see, if you just look at this particular graph, this diagram, essentially if you just draw it like this, let me again draw another part. See, x equals to 1, these curves are there, and x equals to t plus r, they intersect here, okay, and these up till this part they also intersect here, right? So these are the characteristics. See, that's the intersection. In this part, u is of course 0. U is of course 0 here. You don't worry about it. So essentially, you see in this part also, these parts u is 0. This part u is 0. Okay. My issue here is only in this region. My issue here is only in this region. This region. What happens here? Do you understand? Okay, because the curves, projected characteristic curves intersect. Here there is no intersection. You see, here means these parts. Here there are no intersections. All of these areas. Okay, so this area is given by this. This is the same area. Okay, so here there are no intersections. So u equals to 0 here, u equals to 0 here. That was given to us. I don't know what is happening in this area. That is the point which I want to look at. Okay, of course, if there is a shock curve that starts from x equals to 1. Right? So, and what is the speed of the shock curve, that we need to find out. So, how do you find out the speed of the shock curve? For that, we want to use the Rankine-Huggenite condition, right? So, by Rankine-Huggenite condition, again, as I told you, RH condition, whenever I am writing, it means Rankine-Huggenite condition. Okay, I hope I have explained to you earlier also. Okay, whenever we are writing RH condition, okay, I did not explain. Maybe I explained it in the earlier videos. So you see, there are some things which we are always going to use in this course. Whenever I am writing this small phi, most of the times if it is not mentioned, we think of this phi as some function, a particular function, okay, which will be given to us. So in our case, this small phi is, you see, this small phi is the data curve, initial data curve, small phi. Okay, if this phi anywhere in the assignments also, if it is written like this. If it is written like this, this is the capital phi. Okay, so you see, if it is written like this, capital phi of x, let's say, yeah, then you guys already know that is the fundamental solution, right? Of what? Fundamental solution of Laplace equation. Okay, solution of Laplace equation. Again, you also know that if it is written like this, capital phi of xt, if it is written like this, it is the fundamental solution of heat equation. Okay. So do not get confused here. Whenever I am using capital phi in this course, always it will mean fundamental solution until unless it is explicitly mentioned what is capital phi. Capital phi is always fundamental solution. Small phi is always some arbitrary function. Yeah. Okay. Now again, and also RH condition, if I'm writing RH condition, you can also use this in your examinations if you want. You write only RH condition, it means Rankine-Huguenot condition. You don't have to write the whole Rankine-Huguenot condition, okay, just write RH condition. Okay, so the RH condition, what does it give? It gives the speed of the curve, sigma. So I want to draw some curve, this curve, I want to find what this curve is. So sigma is the jump of f of u by jump of u, okay, and f of u here is, see, in this case, this is a Burger's equation, right? So f of u is u square by 2, it is written here, f of u is u square by 2, right? So you see here, it will be given by u minus plus u plus by 2. If you just break it up, it is going to be this, right? Okay, now let's see what happens. See, on the other side, u is going to be 0 here. It is always, u plus is always going to be 0. Okay, so I don't know what is u minus, but u minus also here, from here you can see that I mean, if this has to satisfy in these areas, u minus is going to be 1, right? Right? I mean, because of the initial condition, you see, initially it is getting carried out like 1, okay, up till x equals to 1, it is getting carried out. So I am starting out with the data curve such that I want u to be 0 on the other side, this side u equals to 0, and on that side u equals to 1, because just to match the initial conditions. Okay, so I want u, so u minus is 1, u plus is 0, and by 2. So this is half. So the speed of the curve has to be half. So therefore the shock curve, okay, how do I put it? The shock curve, shock curve. So basically our curve x equals to xi t. If you remember, shock curve is given by, here it is not x, it is x minus 1, because it starts from 1, right? So it means x minus 1 equals to half t, sigma t, right? That's the shock curve. If you remember, sigma is the slope of that. Okay, so essentially what is happening, the slope is half fixed, so essentially what is happening is this shock curve will look something like this. Clear? I hope this is fine. Maybe I can, okay, 1 second, let me okay, let me just draw it properly. Okay, see the shock curve from here, this is x equals to 1, this is the x-axis, it starts from here, it goes on like this. So this is x minus 1 equals to t by 2. That's the shock curve. Okay, why it is like this? Because you see it starts from x equals to 1, yeah, so that is why it looks like this. So x equals to 1, and in this whole region, u plus is going to be 0. Clear? Okay, now I don't know what is u, so I have to find what is u in these parts, right? Okay, so this is a shock curve, I know u plus is going to be 0 here. What is u minus here? I know that u minus here, you see, since there is an initial condition given here, what is the value of u here? It is 1, right? And it is getting carried forward. So on one side of the shock curve, you can write it as 0, and the other side of the shock curve, you can write it as u equals to 1. I hope this is fine. Why? Because of the initial condition. Okay, but is it always 1? No, it is not always 1. It is 1 up till x equals to t. X equals to t. So this line is x equals to t. Okay, so in this part it is 1. Is this clear? See, I mean, we have to worry about this part. This part, in this part, u is 1 because the initial condition. I am taking it to be like this, and on the other side of the shock curve, and I am extending it. Okay, I am extending it up till here. So u is 1 up till in this area. Here u is 0. Here u is 0. In this part, u is 0. Okay, so because on the other side of the shock curve, you want u plus to be 0, u minus to be 1. So u is 1 in this part. Is it 1 here? No. Okay, because there is a rarefaction wave going on. You see, here there is a rarefaction wave going on. Okay, so I don't know what is there there. So for that I have to worry about the rarefaction thing. Now you guys already know that if you have a rarefaction thing, it is g of x by t, where g is f prime inverse, right? And in our case, when f is u square by 2, you guys already know that what is it? This is given by u equals to x by t, right? So in this area, let me draw it like this. This area u is given by x by t. I hope this is fine. U is x by t. You remember last this thing exercise also we did this. Yes, in the last exercise we did this thing. So again, let me just write it down. That of course, I don't know. Oh, okay, of course. Okay, u is equals to x by t in the region, which region? X equals to 0 and x equals to t. Clear? So in that region, after t equals to 1, of course, after t equals to 1, this is going to be u equals to x by t. That is always there. Okay. Now, because you see, now my new shock curve is this. Here it was intersecting, there was a problem, so we constructed a new shock curve along which one side it is 0 and one side it is 1. Okay, now this particular x equals to t, that intersects somewhere, right? This x minus t equals to 3. So see, at t equals to 0, now at t equals to 2, okay, x minus 1 equals to t by 2 and x equals to t intersects. Okay, so again same problem will happen. You do understand? Again, if they intersect, again the same problem will happen. Okay, so and now I hope this is fine. What I'm trying to say. See, if you now, so if you are defining u to be 1 0 in this area whole u is 0. Clear? U equals to x by t in this wedge. X equals to 0 and x equals to t. Between x equals to 0 line and x equals to t line, I am taking u to be x by t. This is the rarefaction thing. That is why I am just doing it like this. U equals to 0 on this area. You know that x minus t greater than t by 2, that area. Okay, this area. Okay, now this area equals to 1 because of the initial conditions are dictating that, right? Okay, u equals to 1 between x equals to t and x equals to t plus x equals to x minus 1 equals to t by 2. Okay, between this area u is equals to 1, that we have. But what is happening here is this. See, if you move forward in this point t equals to 2, let's say this is t equals to 2. Okay, x minus 1 equals to t by 2 and x equals to t, these two again intersects. Okay, when it intersects, what is happening is this. You see, along the there is another the rarefaction. So basically this is the rarefaction wave, right? Here these waves are rarefaction waves. These rarefaction waves, they actually hit the shock wave. This is the shock wave, right? X equals to, see, let me use a different color, I think that will be better. You see, this is the shock wave. Okay, and this is the rarefaction wave. X equals to, see, this is the rarefaction wave. X equals to t, right? X by u equals to x by t here on the rarefaction wave. So basically they get intersects here, right? Now whenever they are intersecting, then also we have another issue, right? How do you deal with that issue? That's the question which we need to answer in this part. Okay, so let's just do that. I hope this is fine. Again, see, I am explaining it to you. It may not be 100% clear to you. What I want you to do is, you take your pen and pencil, sit down with this exact example, okay, and try to write everything down, think about what is happening. Okay, so please do that. I can do my best to teach you, but the thing is, until unless you do it yourself, you won't understand what exactly is the problem. Okay, so here what is happening is, at this point the rarefaction wave and the shock waves intersects. Okay, and now what happens is, so we need this jump now. I have to have another curve something from here, which will actually has to satisfy the Rankine-Hughes condition for our solution to exist, because from this point onwards the solution again does not exist. Okay, so what happens now? intersects, and we have a problem, right? So basically the rarefaction wave and the shock wave intersects. So maybe I can put it like this: the rarefaction wave and shock wave intersects. Clear? Okay, now I have to do all of this all over again. So what we have to do is, now again you see, so from this point, okay, I have to draw another curve, okay, such that u minus is x by t, because you see u is x by t in this part, okay, and u is 0 on this part, okay. So I have to draw another curve. So basically by Rankine-Hughes condition, so I will start with another curve which starts from this point. You understand what I am trying to say? Since it intersects here, I will start with another curve, okay. So what I am trying to do here is this, and the point is given by 2 by 2, 2, 2, t equals to 2, x equals to 2, this point, okay. So so by Rankine-Hughes condition, again Rankine-Hughes condition, okay, what is the sigma here? That is jump of f of u by jump of u, okay, which is given by u minus plus u plus by 2, okay. What is u minus? U minus here it is given by x by t, okay, and what is u plus? It is 0. So this is x by 2t. Clear? I hope this is clear, okay. Therefore you have a new shock curve, okay. So therefore we have a new shock curve. I know this is a little intimidating, but first, if you do it for the first time, but I mean, you just take some time, I mean, give yourself some time, think about what is exactly happening, okay. This is not very difficult thing to understand. We have a new shock curve, okay, this is emanating. So basically we are manipulating solutions, that's all we are doing, from the point 2, 2. Is this clear? Okay, so let me draw the new, okay. So you see, in this part, of course, u is going to be 0. If you remember, u is going to be 0 in this part, okay. See, u is 0 in this part, okay. And so let's say this is 2, this is 2, 2, okay, and x equals to 2 here, x equals to 1 here, okay. Oh, right, now x equals to 1, so x equals to t line goes like this, let's say, yeah, it does not look like x equals to t, but let's just hope this is x equals to t, okay. That's x equals to t, and this line actually x minus 1 equals to t by 2, that intersects somewhere at 2, 2, right. So this line is x equals to, this line is x equals to what is it, 1 plus t by 2, right? Right, clear? Okay, now here u is 0, yes, here u is 0, clear? Here u is x by t, here u is 1, okay, but from here there is an intersection at 2, 2. What do we do now? So to get, okay, so both the lines are gone. Let me just draw another one. Okay, I hope this is fine. Okay, so x equals to t line, this one, x equals to t, let me write it like this, x equals to t, and this line is x equals to t by 2 plus 1, clear? Okay, now this intersects at 2, 2. So from here there is a new curve emanating from here, okay. So let's just assume some curve, okay, some curve emanating from here. What is the curve? The slope of that curve is given by x by t. So therefore since the speed is given by x by 2t, right? Therefore the curve is given by x as a function of t is root 2 Clear? I mean, you just put it in the problem and you can get it. It's not a very difficult thing to see. Okay, I hope this is fine. I'm not calculating all that. I'm just writing it down. Okay, so now the new curve from here, it starts from 2 2. Okay, it starts from 2 2. That curve, it starts from here, and it's so basically some parabolic kind of thing that will go on up. I mean, that will be our new shock curve. This will be our new shock curve. Okay, now, so what is the solution? Let's just write down the solution. Okay, so this is a little complicated now. Let me write down the solution. Okay, so the weak solution. So there are two shock curves. The weak solution are given by u of xt is the first one, if you remember, 0 for x negative, x by t when 0, x lies between x equals to 0 and x equals to t, x by t, right? It is 1 where here you see, where is it? Yeah, 1 in this wedge, this part, okay? So basically between x is between t and t by 2 plus 1, right? And it is 0 when x is greater than 1 plus t by 2. I hope this is actually fine. Okay, this holds for t less than equal 2, right? Because up till t equals to 2, this is true. T equals to 2, up till t equals to 2, this is true, right? After t equals to 2, you have a new shock curve. Okay, so and for t greater than equal to, okay, what do we have? U of xt is given by 0, okay, if x is x negative. Of course, if x negative, I mean x negative is 0, you don't have to worry about it. Again, if x lies here, so x is greater than equal root 2t in this part. Okay, see, I mean, think of this as in this part, if x is greater than root 2t, this is x equals to root 2t, right? That line, that curve. So x greater than root 2t, it is going to be 0 because u equals to 0 in this part. That's not a problem, right? Okay, and u is x by t in this part. Clear? Okay, so u is x by t if 0 less than x less than root 2t, and it is again 0 if x is greater than root 2t. Okay. I hope this is clear to you. Okay, this is the weak solution which we get. Of course, this is a weak solution because I mean, does it the Rankine Huguenot condition? Of course, it holds because you see we have manipulated our solution like that itself. Okay, because we have derived it using those things, so that will hold. Okay, and of course, you guys can check that this is also going to the entropy condition is going to be satisfied, right? So this particular solution is a admissible weak solution. Okay, hence U is a admissible weak solution. Weak solution. Okay, so if you are not convinced, please check it yourself. Okay, but I mean this is the admissible weak solution which we have obtained. Okay, so with this we are going to end this video.